Welcome back, everyone. Now that we've got our statistical sample of data, we need a way to visualize those data within the sample. And so what we're going to talk about next is how we might visualize those data using something called a frequency distribution. A frequency distribution is simply a plot of the number of times that each distinct observation occurs within a statistical sample. So for example, here we have a frequency distribution of a sample of 70 flowers. And you can see from this frequency distribution that 20 flowers were purple, 40 flowers were red, and 10 flowers were yellow. So in a frequency distribution, the height of each bar represents the number of observations within each of those categories. Now, in this case, the data that we were dealing with were nominal data. That is, that observations were categorized and that those categories didn't fall into any logical order. We can also use a frequency distribution to visualize ordinal data, where the categories fall in some logical order. But we have to be careful with ordinal data because if we don't depict the categories in the correct order along the x-axis, we can obscure patterns in the data. So for example, in this plot that I've just shown, the categories are arranged in alphabetical order, but not in a logical order, ranging from never at one end to always at the other, with sometimes in the middle. And as a result, we can't see the patterns in the data. But once we reorganize those bars so that they follow a logical order from never at one extreme to always at the other, then a pattern in the data emerges. So it's important when plotting a frequency distribution of ordinal data to pay attention to the order in which the categories are arranged along the x-axis. We can also plot frequency distributions for numeric data, and in this case, we give them a special name called histograms. So a histogram is just a type of frequency distribution that's plotted for numeric data. So here we have a sample of 32 observations of the number of surviving piglets from 32 different litters. And we can see from this histogram that sometimes as few as 6 piglets survive, but most of the time in and around 11 piglets survive from any given litter. Now in a histogram, it's important to pay attention to what the labels on the x-axis mean. Here we have a situation where we have a count of the number of observations, but it's labeled with a 5 on the left or a 6 and a 6 on the right. So is this the number of observations of 5 or 6? It can be a little confusing. So we need to know the way in which the plots are being created. In the statistical software program R, the default setting is for the bars to be counts of the number of observations equal to or less than the right-hand indicator, but greater than the left-hand indicator. So this bar here indicates that there was 1 observation of 6. There were 2 observations of 5, 4 observations of 4, etc. Now this is true for all of the bars until you get to the last one. And for the leftmost bar, then this is the number of observations less than or equal to 2 and greater than or equal to 1. And that's why we've got an observation of 1 here for a single observation of 1 from our data set. Now with a histogram, these don't need to necessarily follow discrete integer values along the x-axis. The bins of observations can span lots of different ranges that don't correspond to integer values. Here we have a histogram of the body masses of female sockeye salmon from Pick Creek in Alaska. And in this case, each of the bars represents bins of 0.1 kilogram ranges. We can describe a histogram using its mode and its tails. The mode is simply the most frequent observation in a sample. So we can see that in this particular histogram, these values in the middle have the highest bars, they're the most frequent, and as a result, we call them the mode. At either end of the histogram, we have what are called the tails. The left tail of the histogram over here, and the right tail of the histogram over here. Distributions coming from histograms can have a single mode and be called unimodal. They might have two distinct peaks or modes, and we call them bimodal. Or in some cases, there are more than two modes, and we refer to the histogram as multimodal. Now, whether a histogram is unimodal, bimodal, or multimodal can really depend on the size of the bins that we use to characterize the observations. Here we have that same data set of the body masses of sockeye salmon in both of these histograms. And all I've done is to change the size of the bin along the x-axis. This histogram has bin sizes of 0.1 kilograms wide, whereas in this example on the right, the bins are much larger. Each bin represents a category or a range of 0.5 kilograms wide. And the degree to which we can see patterns in the data can really depend on the size of those bins. So it's important to pay attention and try different bin sizes to potentially reveal or determine whether the patterns that we're seeing are perhaps specific to the bin size that we've chosen. So in summary then, we can use frequency distributions to show the number of distinct observations of each value in our sample. Histograms are a particular kind of frequency distribution that we plot for numeric data. And from these histograms, we can describe different aspects of a distribution. For example, the mode or the most common value of the distribution, and the range of values across the x-axis as they reach the tails. In the next video, we'll talk about some quantitative ways that we can describe data in a sample.